I promised you that I would spare you the math until after we knew a little bit about the kidneys. So we've done filtration, we've done reabsorption and secretion. Now we'll do a little bit of math. And I'm having feedback problems, aren't I? Can you hear? Am I good? Okay. So now, but we're gonna go through it extremely slowly, and it's not going to be difficult at all. Okay. So what we're going to deal with is the concept of clearance. And let me start by reading this case. We're on lecture 6, page 1. A 15-year-old 70-kilogram male is admitted in the late afternoon with a complex problem. His serum creatinine was high, and renal failure was suspected. And we've already kind of been through this. I think most of you are aware that serum creatinine can be indicative of renal failure. This is too loud, isn't it? Even I'm hearing this. Okay. So a 24-hour urine chemistry was ordered at 1 a.m. and the results came back at 3 a.m. on the following day. We're going to work with some of these numbers. We're going to try and determine a creatinine clearance. But at the bottom, this is a true story at the bottom. One of our past students said, Dr. Rowe, they make us do this stuff. So why didn't you tell us it was important? The lab can compute an endogenous creatinine clearance when the day staff arrives at 8 o'clock. However, the patient's physician wanted an immediate estimate of renal function and asked the resident to make the calculations. So you know, as residents, you're still peons, right? It takes a while before you get the respect that you deserve. Yes? So we're going to be able to do that by the end of the day. So I'm still using that antiquated term, renal failure. So renal failure was suspected, and you can conclude that from the creatinine. But let me tell you, this guy's got chronic kidney disease, and there's no doubt about that. Why am I saying that? He's 15. Nope. I'm trying to follow that logic, though. Oh, no. Creatinine? No, creatinine could be up because of maybe rhabdomyolysis or something like that. So it's suspected, but... Protein? Who said that? Oh my gosh, Morgan. Morgan's on the money today. Since we spent the whole of yesterday going through that, I wonder why it took so long. Sorry. It's early here. It's not early, it's 10 o'clock, it's middle of the day. Yeah. Okay. Yeah, that's a lot of protein that's in the urine. Okay, so let's flip the page. And let me just start the definition of renal clearance. Oh, let me tell you where we're going to try and get to. We're going to determine clearance of a substance X, whatever that is, and it's going to equal U concentration of X V dot all over the plasma concentration of X. Okay, that's where we're going to try and go. The nomenclature is a little different in this branch of physiology. So clearance of X, this is the concentration of X in the urine, the volume of urine produced per unit time, and this is the plasma concentration of X. That's where we're going to try and get to. But I'm going to take a little while to get there. So what is clearance? I've got a definition there in bold. It's the volume of plasma which is completely cleared of a substance per unit time. So just to do a demonstration, I have here 1 litre, and I put 10 milligrams of red stuff in there. Oh, I'm male, so that's red, okay? I told you I was having a slow day today. I cleared it. What's the clearance? Give me a value for the clearance. I had 10 milligrams of red stuff in a litre. What's the clearance? 1 litre! Who said that? It wasn't Morgan, was it? Pass it over. Come on. Pass it over. 1 litre. Yeah, so just in very simple terms, although we got rid of the red stuff, it's the volume in which it resided in the first place which is the clearance. So we're clearing 1 litre. Let's get much more complicated. Same thing, 10 milligrams of red stuff in 1 litre. Okay, bear with me. Best I could do was get rid of half of that red stuff. You can see exactly half's gone, right? Yeah. Very good. The clearance is? Half a litre, yes, yes. Okay, good. So that's the concept of clearance. And let me clean up just a little bit here. Don't let me use that handkerchief again. Okay, so let's try to put this into some usable terms. So there's my kidney. Did I? The batteries have gone. I think. Okay, that should be back now. Could you keep an ear on it, because I suspect the batteries are gone and it may go again. When I went into my pockets, I might have turned it off, I suppose. Thank you. So let's have a renal plasma flow of 600 mils per minute. So that's our volume, 600. In that plasma, I've got 6 milligrams in that 600 mils. Now, as it goes into the kidney, you can excrete stuff or you can return to the plasma, right? So let's assume in this first example that 6 milligrams were excreted and 0 were returned to the plasma. And that's pretty close to feasible. Can you figure out what the clearance is? It's the volume that was cleared per unit time in this case. So in 1 minute, I'll try to do better. I'm so burdened with all these microphones. What is the volume that was? It was totally cleared, wasn't it? So it's 600 mils. Okay. So in this case, if this happened, then the clearance would be 600 mils per minute. That's the volume. Okay. That 6 milligrams was in that 600 mils, and it was cleared. Good? Okay, let us say that this didn't get excreted at all, and 0 milligrams got out here, and all 6 milligrams was returned to the plasma. The clearance would be 0. Yes, okay. So in this case, the clearance would be 0. Let us now get incredibly complicated. It's the same 6 milligrams in 600 mils. 3 milligrams were excreted and 3 milligrams were returned to the circulation. And I think by now, I think everybody realizes that the clearance is going to have to be 300 mils per minute. Okay, good. So the concept is clear. Can we do this mathematically? Okay, so let me. Oh, yeah. Okay, there's my 600 mils. And there's the 300 that was returned to the circulation. And there's the 300 that got excreted. Okay, so we're kind of interested mathematically in determining this volume, yes? So volume equals mass over concentration. So the mass is 3 milligrams. So what's the concentration? Well, we know this volume should be 300 mils, right? 300 mils, and that's per minute. And our math had better get us to the same value. So what's the concentration? Okay. 6 milligrams per 600 mils, 10 milligrams per liter, right? But we're working in, okay, so it's 10 milligrams per liter. I haven't lost anybody yet, have I? Okay. So how many milligrams per mil? One, two, three. So it's 0.01 milligrams per mil. Yes? And if we got it right, 3 over 0.01 should be 300. And I think it is. Okay. All I've tried to do here is take the concept which we understand very well, and I just converted it into a mathematical expression. Okay. So we know it was 300 mils per minute, and when we calculated it according to this formula, it was 3 milligrams, and I should 3 milligrams per minute over 0.01. Okay? So 300 equals 300. Anything I need to go through again? Well, I haven't quite got to that end expression, although some of you will probably already see it. Let's do case 9, the one that we just talked about. Can I erase this, or do I need to leave some of this up? Golly, and I thought I was having a rough day. I'm not getting any response. Okay. So, rewriting that again, clearance, volume per minute, which is the clearance, equals the mass that's excreted all over the plasma concentration. So this is the plasma concentration of creatinine, and this is the mass of creatinine excreted. So the values that we had were, the mass excreted was 0.8 grams per 24 hours. The plasma concentration was 4.4 milligrams per deciliter. Now, the thing that we inevitably have to do with clearance calculations, which will come up on STEP exams, it's almost a guarantee, like death, taxes, and clearance calculations come up on STEP exams. Okay, so we're going to have to deal with the units. Let's convert these units. Okay, we've got milligrams down here. Let's make that milligrams. How many milligrams in 0.8 grams? I know, it's a complicated. Take my word for it, it's 800 milligrams in 24 hours. We don't use deciliters, so a lot of things clinically are still measured in concentrations per deciliter. Glucose is, creatinine is, a whole bunch of things are. And it's really kind of an old-fashioned concept. Many 40 or 50 years ago, all solutions, before we really got into molarities and the such like, all solutions pretty much were measured as concentrations per 100 mil. It kind of gave you a percentage, which was useful in those days. But for us, it's not a very useful volume. So let's convert it to, what, liters or mils? Let's convert it to liters. 4.4 milligrams per deciliter, how many per liter? Somebody's got to say, come on, this is good, this is good. Where am I? How many grams per liter? Nobody's hungry. Thank you. Who said that? You did? Thank you. So what I'm trying to figure out is, do the rest of you not know, or are you just shy? Okay. Shh. Okay. Look. Let me write it up first. So that's now 44 milligrams per liter. Look, and I know some of you don't have a background in science. Some of you have backgrounds in the arts, but you kind of have to get to grips with some of this, okay? So I mean, these are fairly straightforward quantitative concepts, and you can be sure that The shelf exam tries to trick you with units, okay? So you need to be able to make these conversions. Anyway, I don't know the exact value here. Let's see, I did calculate it somewhere. That comes out to 18 liters. Comes out to 18 liters per 24 hours. Let's call it a day. Okay. So that was the creatinine clearance that resident had to calculate. I think you already have a hint. I'm trying to keep my hands away from the microphone. I think you already have a hint that the creatinine clearance has some relevance in renal physiology. And we'll learn later that it kind of approximates GFR. So if GFR is 18 liters per day, gosh, that sounds like a lot, doesn't it? Is it low? Yes, it's way low. It's about a tenth of what it should be. So GFR is usually, or creatinine clearance is usually around 180 liters per day. So this guy surely does have a grossly diminished glomerular filtration rate. Okay, we haven't quite got here yet though, have we? So there's your 900 mils of urine. And I'm telling you that it had 800 milligrams of creatinine in it. How'd you do that? Well, you know you can measure the concentration. The volume's pretty easy, it's 900. Let's see. Mass equals concentration times the volume. So this mass equals the concentration times the volume. Yeah? So this expression will give us 800 milligrams in 24 hours. Okay. Got it? Good. Now, look, I apologize. For some, this is too simple and too straightforward. But not everybody has a background in math, so I went very, very slowly. So understand that everybody is at a different level, and some of you I've ticked off by doing something that's too obvious, and some of you may struggle to figure out what I've just done. But either way, so long as we all get to the end point, that's good. So if you're super smart and you didn't need that kind of explanation, bear with me because we're trying to get everybody up to speed. Questions? That's the expression. So you're thinking, well, Rowe? Rowe? Hand in my pockets. We just have to do these calculations for the test, right? So we just remember the formula. And why did you go through all this mathematical derivation? In general, there are things that I don't think you need derived for you. But the concept here, I think, is significant. And we just spent, what? We just spent 20 minutes going through that. I think it's a good investment for the future. Okay. So let's flip the page. So now we've got clearance values for various substances. If I went to all this trouble to show you how to do clearance, then there must be some utility. And I think you're already getting the idea that creatinine clearance has some utility. But let's try and determine some clearance values. And I'll go back to this idea of a scale where the volume is, up here is 600 mils per minute. And here is 0. And along here, well, let's just leave that alone for right now. So let us start with something that behaves like that. Something that is totally cleared or extracted from the plasma. What will its clearance be? We just did this 10 minutes ago. What would the clearance be? 600. Okay. So if we could find a substance that was completely removed, its clearance would equal renal plasma flow. So what I'm saying is, and there is a substance that comes pretty close, para-aminohippuric acid, which we'll cover more later. I'll just put PAH, para-aminohippuric acid. So if we've got this substance that we could totally extract and excrete all of it, then we could calculate its clearance and it would give us the renal plasma flow. Okay. What about glucose? What's the clearance of glucose? Yeah, usually 0. So glucose, 0. And this is PAH. Okay, because glucose is totally reabsorbed and none is excreted, so the clearance has to be 0. All right, this is worth 2 goodies out of the basket of goodies. Which, did somebody go home and take the goodies with them? Oh no, they're still there. Okay. Ammonium has a clearance that's way above 600. Somebody explain how that could possibly be. Secretion, not the correct answer. It may be secreted, but it's not the correct answer. It's what?
Sweat or something?
Sweat? No. Say again? Cleared in other ways? No. Is it what? It probably is, but that's not really the answer. How can you clear plasma of more stuff than it was in it in the first place?
You make it.
You make it. Who said that? Morgan, you are amazing today.
Why do you doubt me?
Well, I tell you why I doubt you, because nobody else got it right. So how can I not doubt you? How could I doubt you? I'm sorry. Double negatives. Yeah, I mean the only way, and this is just conceptual framework for you. The only way you could actually excrete, and I swear I didn't touch it. The only way you can excrete more than you got in the first place is you have to make it in the kidney. And so yes, the kidney makes ammonium. Good. Now, let's come down to 100. And we'll call that the glomerular filtration rate. what would a substance have to do to have a clearance that's equal to the glomerular filtration rate?
All of it's got to be filtrated and then secreted.
Yes, I like that. I would qualify that a little bit. All of it has to be filtered, and you said none secreted, and one other thing, not reabsorbed. Okay? In other words, to put it a different way, whatever was excreted, whatever was filtered was fully excreted. Let me put that another way. The only way it could get into the urine was from what was filtered, because none of it was secreted and none was reabsorbed. Is that closer? Okay. So indeed, if we had a substance like that that wasn't secreted and wasn't reabsorbed, like inulin, its clearance would equal the glomerular filtration rate. Okay? So you're beginning to see the utility of understanding what renal clearance is. If we can find the right substance and know how it behaves, we can predict aspects of renal function. Okay. All right. Now, let's go back to glucose. We kind of glibly said that glucose is 100% reabsorbed, but not in everybody, right? Diabetics, for example, there is spillover into the urine. Will that affect the clearance of glucose? Yes. Okay. So, if we plot the plasma concentration along here, so now the concentration is increasing. As you get more and more glucose, you eventually reach a threshold, and the clearance would go from 0 upwards until eventually it would meet this. Okay. What about inulin? So this is kind of a trick question. Sorry. This is kind of a trick question. I'm going to have to walk around like this. What will happen if I increase the plasma concentration of inulin? What will happen to its clearance? It will stay the same. Yeah. And the reason is that it doesn't really matter if we double the GFR, we're going to double the amount of inulin that's filtered, but we'll also double the amount that's excreted, and so it's still indexed to the amount that was filtered. So indeed, inulin doesn't change. And this will eventually come up to here. That is assuming that it doesn't affect renal function. Probably out here, it might have an osmotic effect, but we're not going to worry about that. PAH. So the idea is that PAH pretty much reflects renal plasma flow. But PAH has to be fully secreted in order for that to be the case. And as you know, most transport mechanisms are saturable. And we saw yesterday a saturation curve for PAH And after a while, you get to a point of maximum secretion. When you get to that point, you can no longer secrete 100% of it. Okay? And you saw the graph yesterday, but the clearance has to fall because it now violates that assumption that it was all excreted because we can't fully secrete it. Okay? Now, that probably seems obvious the way that I've just explained it, but believe me, for whatever reason, medical students struggle with this concept. And so if you get a test question on this, a lot of people want to say, well, it goes up or it stays the same, because it just intuitively it feels that way. But the reality is that the plasma, as the plasma concentration increases, the clearance has to go down. Okay? So why did I do all this stuff? Costanzo is usually pretty darn good at telling you everything that's likely to come up on STEP exams. She doesn't actually have this in her book. But I can tell you that it has come up on STEP exams. The STEP exams want you to be able to reason what happens if you change the plasma concentration of these substances, what happens to the clearance, just to see if you understand the concept of clearance. So I think there's a very high probability that the STEP exams will test you at this level. And I think it's the only thing I've ever seen in Costanzo that she never... I think Costanzo actually wrote a lot of board questions at one time because she seems to be very familiar with them. But for whatever reason, this concept just didn't appear in her textbook. And I also looked in the BRS series. It's not in there either. Anyway, so everybody good with this? Okay, let's go to the next stage. All right, so we're on page, the next page, whatever that is. Does it have a number in your handout? No? Okay. And I think we can go through this fairly quickly because we've already covered it to some extent. We're going to measure the clearance of inulin, and we're going to try to determine that it reflects the GFR. So, oh, by the way, this is your M1s. You will never, ever do this except for the STEP exam, okay? So it is not used in medicine at all anymore, except in, research studies. However, as M1s, you're expected to understand this. So the first three items, I think, are pretty straightforward. If the clearance of inulin is to measure GFR, it has to be freely filtered, and this is in the handout, and I don't need to write it on the board, do I? It has to be freely filtered, not reabsorbed, and not secreted. So in other words, whatever is filtered has to be excreted. Okay? So the amount filtered equals the amount excreted. And if you want to do some mathematical magic, and I suspect that if I look closely, a lot of you would say no, what's the amount excreted? And that's inulin. What's the amount filtered? Okay, so they equal. Can you divide each side by pi? Okay, so mathematically it works out too. Okay. So I've got a couple of other additions there. Can't be synthesized by the kidney, can't be degraded by the kidney, and it can't alter renal function. So why don't we use this clinically? First of all, inulin has to be infused. And I don't know whether you're aware of it, but infusing a compound to generate a constant plasma concentration is actually pretty darn difficult. Also, you're going to have to collect it from the urine, which, if you want to be accurate, means you're going to have to catheterize the bladder, wash it clean, have a clearance period where you collect urine for half an hour or 3/4 of an hour or whatever it is, and then take the catheter out. And there ain't no way we're going to do this to patients unless there's an absolute need. Okay? So, not used for that reason. So, we'll talk about it a little later. Creatinine is an endogenous compound. We don't have to infuse it, and it kind of comes close to the assumptions that we just mentioned. So, and I'll talk about that a little more later. There are other methods for assessing renal function. There are other compounds like radio-labeled iothalamate, radio-labeled DTPA, radio-labeled EDTA, and you can basically just measure how quickly they're removed from plasma. So there are alternatives that are a lot more simple. But for the most part, once you've got an index of renal function, we have other stuff available like renal scans, X-rays, arteriography, even sonography of the kidneys. So in modern medicine, we tend to have other ways of assessing renal function, and certainly inulin is not used. Okay, one last thing before we take a break. One last thing. Let's talk about the measurement of clearance for PAH, for pH for renal plasma flow. I think we've already been through the assumptions. I guess I get an echo if I do that, don't I? We've already been through the assumptions. However it gets into the urine, technically if 100% of what was presented to the kidney gets into the urine, then the clearance of PAH will be the renal plasma flow. The problem, we have to infuse it. The problem is that there is a Tmax, and if you infuse too much, you will violate that assumption that you can secrete it all and nothing works. So that's one thing. The other thing is that I kind of lied when I said it was 100% extracted. Okay, what a surprise! Rowe lied. Well, I kind of elaborated on the truth of the matter. I exaggerated. So there's probably about 85 to 90% extraction, which is still pretty good. Now, the way that we reason that is, well, okay, it's still a pretty good index of renal plasma flow because renal blood flow actually includes the perinephric fat and some other structures, and so pretty close, the clearance of PAH represents the blood flow to tubular tissue or to glomeruli. So that's why we use the term that the clearance of PAH is the effective renal plasma flow. In other words, it's the effective flow that bathes the tubular tissues. Okay, so that's just terminology. I wouldn't like to make a big deal of it, but it's in the textbooks, and you might be tested on that. Okay, so one last thing. Who loves the Fick principle? Tough. Of course, it's going to haunt you. Sorry. So look, you did the Fick principle in cardiovascular physiology, and although we don't use it as such in cardiovascular, you still need to know it. And about 10 years ago, I told students, you can also do renal plasma flow with the Fick principle, but there is no way the shelf exam will ever test you on that. I was wrong. Okay? I think, well, it doesn't really matter what I think. I think that's more than you need to know, but to some extent, well, those people that do the shelf exams, they know better than I do. So they're saying you need to know the Fick principle for renal physiology. I've written it down there in the handout. I'm not going to go through it because it's a derivation that I don't think you need to know. Costanzo does an elegant derivation if you're interested. Okay? Basically, the Fick principle just says what goes in must come out. And it's just a mathematical expression of that. So look it up if you're curious. But I'll tell you what I'm going to do. Even though I don't think you should be tested on it, because the shelf exam has tested you on it, I guarantee you I will ask you a question on the Fick principle on the exam. Okay? So that's just kind of to get you up to speed on using the Fick principle. Okay? All right. We'll take a break. Any questions? Let's take a break and start again on the hour.